Hi. In this video, we will discuss some of the ways that atoms and molecules bond and bind to each other. These topics will be reviewed to many of you. It'll be new to some, but it's important that we all get on the same page so that we can have more discussions. We'll talk about covalent and ionic bonds, and we'll talk about hydrogen bonding, which is a particular type of electrostatic interaction. We'll talk about hydrophobic effects, which is one way that molecules will separate and organize. And we'll emphasize two rules of thumb, which we'll talk about many times in this course. One is about electrostatics. Opposite charges attract and like charges repel. And the second rule of thumb is about the hydrophobic effect, which is basically saying that oil and water don't mix. To start the discussion, we want to talk about how some atoms can be held together, either by covalent bonds or ionic bonds. In the first case, they share electrons. In the second case, they will transfer electrons to each other. Here we have very simple schematics of covalent bonding on the left and ionic bonding on the right. The trick is, how do you get two positively charged nuclei to be close to each other? It's a problem because, as we've said, like charges repel. For covalent bonds, or the sharing of electrons, you form an excess of electron density in between the two positively charged nuclei. For each atom, you had a spherical distribution, and when the two nuclei come close to each other, you will have a distribution in which the electrons are concentrated in the region between the two positively charged nuclei. And that's a stable electrostatic configuration. And that is what we think of as a covalent bond. In the other case, you have a transfer of an electron from one atom to another. Now you have a positively charged atom interacting with a negatively charged atom. And again, this is an ionic bond. There is an attraction between the two, and they will be in close proximity. A prototypical ionic bond is one seen between sodium and chlorine. Sodium atoms will donate one of their electrons to chlorine. This gives both ions complete outer valence shells, 8 electrons in the valence shell, which is a stable atomic configuration. And now, sodium and chloride ions can interact with each other. In the absence of salt, they can form regular grids, which are visible here as salt crystals, when all the water it was originally in dissolved and has evaporated. On this slide, we'll talk about some of the strengths of interactions of molecules and energy content in general. We'll start by pointing out the energy of a carbon-carbon bond, a single bond, is about 83 kilocalories per mole at room temperature. And compare that to the average thermal energy at room temperature, kT, which is about 0.6 kcals per mole. So you can see that at room temperature, it's extremely unlikely that a carbon-carbon bond would ever break due to just average thermal motion. Non-covalent bonds in water, like hydrogen bonds, can be from 1 to a few, 2 or 3, kilocalories. And average thermal motions are large enough to disrupt those. When we hydrolyze a molecule of ATP in the cell, we will get about 11 to 12 kilocalories per mole from that, versus approximately 670 calories for the complete oxidation of a glucose molecule. Since we won't talk much more about individual atoms, I just want to get this in now. On this slide, we see the elemental atomic composition of human bodies in red, and that we are comprised primarily of 4 atoms: hydrogen, carbon, oxygen, and nitrogen, with many other atoms contributing small amounts. With covalent bonding, there are some different properties between single and double bonds. Free rotation is allowed around single bonds. Double bonds are stronger, and they are constrained. You will not get rotation around this double bond, and these atoms will all be confined in a plane. We are primarily carbon-based creatures. As you can see, carbon is tetravalent. It can make 4 bonds. As you can see for this carbon atom, it is bonded to 2 other carbons and 2 hydrogens. This can sometimes be drawn like this, without explicitly drawing in the hydrogens. Or like this, where every vertex is a carbon atom. And it's always implied that there are as many hydrogens as there are needed to be to make each atom tetravalent. Aromatic compounds such as benzene have multiple connected double bonds, following the 4n+2 rule for electrons in a cyclic structure. There is an extra resonance between these two forms, and the most accurate benzene structure is a combination of these two structures, and it's often depicted as a circle. We have certain words that indicate different chemical groups. As shown here, a methyl group, a carbon and 3 hydrogens attached to another heteroatom. If we talked about these 2 carbons, this would be an ethyl group. If we talked about these 3 carbons and all the hydrogens, that would be a propyl group. So the different nomenclature is saying something about the number of carbons in this case. In addition to pure hydrocarbons, you can also have carbon-oxygen bonds. In this case, the hydroxyl group, which is an alcohol. A slightly more oxidized version of this carbon is a carboxylic acid, which in solution is a negatively charged molecule, as it will lose a hydrogen ion to water. Some covalent bonds can have partial ionic character. That is the case with water. There are covalent bonds here between oxygen and hydrogen, but since oxygen is more electronegative than hydrogen, it will attract more of the electron density closer to its nucleus, and therefore there will be a buildup of negative charge on the oxygen atom. You'll have a partial negative charge on the oxygen atom and corresponding partial positive charges on the hydrogen atoms. This will result in a net dipole moment for this molecule. Contrast that to a case of oxygen, molecular oxygen, where the atoms are identical and therefore have completely equivalent electron sharing. There will be no partial positive and negative charges on this molecule. Now we'd like to discuss a type of electrostatic interaction that occurs so frequently in biology that it's given a special name. It's referred to as a hydrogen bond, but it's really nothing other than straightforward electrostatics. You have an electrostatic interaction between a partial negative charge and partial positive charges, and those attract. They want to be as close to each other as possible. You also have the repulsion of partial negative charges with partial negative charges, which is what gives this stable configuration of atoms a sort of linear geometry. If you were to move this molecule at an angle, and that would make the hydrogen-oxygen bond here, you'd be bringing these partial negative charges closer to this partial negative charge, and that is energetically favorable. So you will automatically get a linear conformation. The distances between the oxygen and the hydrogen for the covalently bonded portion is roughly 1 angstrom, and about 1.7 angstroms between the oxygen and the hydrogen that are participating in the hydrogen bond. Now the oxygen has 2 lone pairs which can participate in hydrogen bonding and 2 hydrogens. So each water molecule has the ability to take part in 4 hydrogen bonding events. And that is indeed what happens. Most of the time these are transient in liquid water because thermal motions are of comparable energy and able to disrupt them. But when you freeze water down into ice, thermal energy is lower and you freeze in this very organized structure between water molecules. And this is a contributing factor as to why ice is less dense than liquid water and rises to the tops of lakes, for instance. Now when you dissolve a hydrophilic atom or molecule into water, it has the ability to be solvated. A positively charged sodium ion will attract the partially negative charges on the oxygen, forming this configuration. If you put in a negatively charged chloride atom, this attracts the partial positive hydrogens, and so you can say that these ions are solvated. They're stabilized. In the third case, you have an organic molecule with the ability to form lots of hydrogen bonds. And these water molecules can exchange with one another quickly. And so this is an energetically favorable situation. Now in the case of hydrophobic molecules are not able to engage in hydrogen bonds. Only hydrogens that are connected to electronegative atoms like oxygen or nitrogen can participate in hydrogen bonding. Hydrogens bonded to carbon atoms cannot participate in hydrogen bonding because there is not a great electronegativity difference between the hydrogen atom and the carbon atom. And so you won't have partial positive and negative charges on the two atoms, and therefore you won't have the ability to form the electrostatic interactions that we call hydrogen bonds. Since hydrophobic molecules are not able to participate in hydrogen bonds, what you have is water molecules nearby which are not making bonds, which is what they would want to do energetically. And they're also not able to rotate around freely. So this is an energetically unfavorable interface, and one that thermodynamically will be minimized. And we see an example of that minimization here. We have two hydrophobic methyl groups which have energetically unfavorable interfaces with a large amount of solvent. By clustering these two methyl groups together, you're minimizing, in essence, the surface area of these molecules. And so you're minimizing the energy of the system, although it's primarily an entropic consideration, because here you're restraining many water molecules, whereas here there are fewer water molecules that have their conformations restrained. You are increasing the entropy of the solvent and system by clustering the hydrophobic molecules together. This is the source of the hydrophobic effect. Hydrogen bonding plays huge roles in the shape of proteins and nucleic acids. In this case, we have hydrogen bonding between backbone atoms, perhaps of an alpha helix. We'll see examples of this in future lectures. And of the two base pairs, nucleic acid base pairs, a C and a G interact with each other through a number of hydrogen bonds. So when proteins bind to each other with their convoluted shapes, what they're doing, they have complementary shapes and charge patterns. Here you can see electrostatic interactions between the two. There are also regions of the two proteins that are neither positively nor negatively charged but have hydrophobic areas with complementary patches on the other protein. These hydrophobic interactions will also contribute to the strength and specificity of interactions of the two biomolecules with each other. Most of this video was a very quick run through different types of bonding considerations, but I want to highlight two rules of thumb which we'll use over and over in this course, and from which you can reason a great deal about biological phenomena. And they are very simple. One is that opposite charges attract and like charges repel. This is an electrostatic interaction, which is an enthalpic contribution to the free energy. The other rule we can summarize as that oil and water don't mix. This is what gives rise to the hydrophobic forces that we just depicted, and these are primarily entropic contributions to energy stability. So in this video we've talked a little bit about covalent and ionic bonding. We've talked about hydrogen bonding, hydrophobic effects, and two very important rules of thumb. Thank you for listening.